Welcome back, everyone. Today, we're going deep, really deep into a survey paper all about securing machine learning models in healthcare.
Sounds exciting.
Yeah, it is,
Yeah.
especially given our listeners' expertise in, well, machine learning and data science and all that mathy goodness. We're aiming for like a professional overview. Concise, but comprehensive. You know what I mean?
Absolutely. Hitting all the key points without getting too bogged down.
Exactly. So this paper, it's not just about how cool and amazing machine learning is in healthcare, which it totally is,
Yeah.
but also, the potential vulnerabilities, the weaknesses in that whole machine learning pipeline.
The things that can go wrong.
Exactly. And Beatty, importantly, what we can do about it, like what solutions are out there to make sure everything's, well, secure and private, all that good stuff.
Right. Building trust in these systems is key.
Totally. So the paper kicks off by laying out the potential of ML in healthcare. And it really touches on everything. We're talking prognosis, diagnosis, treatment, even those like clinical workflows.
A pretty broad overview showing just how far-reaching ML is becoming.
It really is mind-blowing. Let's start with a prognosis. The paper highlights how ML can actually predict disease progression. It's kind of wild when you think about it.
Yeah, like imagine using ML to catch cancer super early or figure out who's going to respond best to certain medications. It's personalized medicine, right?
Totally. Predicting how a disease will unfold. So powerful.
Huge implications for patient care.
Then there's diagnosis. I mean,
Mhm.
ML is making waves here, especially when it comes to those electronic health records, EHRs.
EHRs, a data goldmine. The paper also goes deep into medical image analysis, where it's all about deep learning.
And CNNs specifically, right? Convolutional neural networks. They seem to be the stars of the show here.
Yeah, CNNs are incredibly versatile. They're being used to, well, enhance images like denoising and super resolution.
Making them clearer.
Exactly. So doctors can make faster and more accurate diagnoses. Techniques like JANs are being used for this, for things like faster MRI scans.
It's almost like, I don't know, giving doctors superhuman vision or something.
That's a good way to put it. And it's not just enhancing images. CNNs are also being used to, detect things like tumors.
Oh, right, like pinpointing abnormalities.
Yep, and classifying lung diseases.
Mhm.
The paper even talks about transfer learning, how a model trained on one set of images can be applied to a different but kind of similar task. There are limitations, of course, but the potential is huge.
It's like teaching a computer to, I don't know, recognize different breeds of dogs after learning to identify cats.
Yeah, something like that. But it goes even further. We're talking segmentation.
Segmentation.
Yeah. So basically you use CNNs to quantify abnormalities. It's about partitioning images, dividing them up to figure out the extent of a problem. UNet architecture is a popular choice for this.
So we're not just identifying a tumor, we're measuring it too.
Right, getting precise information. And then there's image reconstruction.
Using ML to actually create images.
Yeah, from raw data, like what you get from MRI and CT scans. CNNs are used here too, along with autoencoders and JANs. And it really speeds up the whole image creation process.
That's crucial, especially when time is of the essence.
Absolutely. And the paper also talks about image registration, which is, well, aligning images.
Aligning. What for?
Oh, lots of reasons, like comparing images from different time points or, fusing images from different modalities. It's useful in things like surgical planning, helping doctors plan those complex procedures.
So they can see things from multiple angles, literally.
Yeah, exactly. And then we have image retrieval.
Retrieval.
Basically, it's about managing those massive medical image databases, finding the right images quickly and efficiently. And modality classification is key here.
So we can search for, say, all the x-rays of a particular patient.
Exactly. And then the paper moves on to treatment and how ML is transforming that side of things, too. NLP, natural language processing, plays a big role here.
NLP, that's all about language, right? So how does that fit in with treatment?
Well, think about radiology reports. They're full of text, right?
Tons of it.
And NLP, along with ML, can be used to generate those reports automatically.
Wow, like an AI assistant helping radiologists.
Exactly. It can be a huge time saver, especially when they're dealing with a high volume of patients. More efficient care all around.
That's amazing. And then there's the whole world of wearables and sensors, real-time health monitoring. It's like something out of a sci-fi movie.
It is pretty futuristic. Imagine ML analyzing data from those devices, tracking your heart rate, your sleep patterns, all sorts of stuff.
And catching potential problems early on.
Exactly. It's like having a constant health checkup without even going to the doctor. But of course, there are privacy concerns.
Yeah, all that data being transmitted to the cloud. It's a bit unnerving.
Definitely something to think about. We need to make sure patient privacy is protected, even with all these awesome technological advancements. And then the paper dives into clinical workflows, which might sound a bit, I don't know, less flashy, but it's where ML can really streamline things.
Like making those everyday tasks easier and more efficient.
Exactly. And it starts with disease prediction and diagnosis. The paper actually mentions a study where ML was used to predict and diagnose diabetes, and it showed some pretty impressive results.
Wow, so it's not just theory, it's actually working.
Yeah, early and accurate prediction is key for managing chronic conditions like diabetes. And then there's computer-aided detection or diagnosis, PAID and CADx. It's basically ML helping doctors interpret medical images.
IBM's Watson is a big example of this, right?
Yeah, but really any application where ML automates image or signal analysis can be considered CAID or CADx. And it's not about replacing doctors, it's about giving them an extra set of eyes, helping them make those tough decisions.
Like having a supercomputer working alongside them.
That's a good way to visualize it. The paper also talks about clinical reinforcement learning, or RL. It's about using algorithms to personalize treatment.
So tailoring treatments to each individual patient.
Exactly. The paper uses the example of sepsis treatment in ICUs. RL can help optimize those treatment strategies in real time, which can be life-saving in critical care settings.
It's like having an AI-powered co-pilot in the ICU, guiding doctors toward the best course of action.
Great analogy. The paper also touches on how ML is being used to, model clinical time series data. Things like predicting clinical interventions in ICUs. They use things like CNNs and LSTMs for that.
Analyzing all that data over time, looking for patterns that might indicate a need for intervention.
Exactly. And then there's clinical natural language processing, or clinical NLP. It's about using NLP to extract information from clinical notes.
Those notes are often packed with crucial details, but they can be so time-consuming to read through.
That's right. And clinical NLP can automate that process, pulling out the key information and making it easier for doctors to access. It's like having an AI assistant summarizing those lengthy notes.
Wow, that would save so much time and effort.
Exactly. And finally, the paper talks about clinical speech and audio processing.
So like speech recognition for documentation.
Yeah, that's one application. It can also be used to reduce clinician workload and even enable new diagnostic methods. Some systems can even transcribe conversations between doctors and patients, which can be a huge time saver for documentation.
I've heard of systems that can analyze a patient's voice to detect subtle changes that might indicate a medical condition.
Right. It's like having an AI that can hear things human ears might miss. So yeah, we've covered a lot of ground here. It's clear that ML has the potential to completely revolutionize healthcare.
It's mind-blowing, really. But, of course, there's always a but, right?
There is. As with any powerful technology, there are risks and vulnerabilities. And the paper does a great job of diving into those potential weaknesses, starting with data collection.
Right, because even with the best intentions, things can go wrong, like what the paper calls instrumental or environmental noise.
Basically, it's about those little artifacts that can get introduced during data collection, like if a patient moves during an MRI scan.
Ah, so seemingly minor issues can actually have a big impact.
They can, especially if they lead to misdiagnosis. It really highlights the importance of data quality and having those robust data collection protocols, making sure everything is done right from the start.
Garbage in, garbage out, as they say.
Exactly. And then there's the issue of what the paper calls unqualified personnel.
Now, I don't think they're saying anyone is unqualified, but it's more about the need for people with expertise in both healthcare and in machine learning, right?
Right. It's about having the right team.
Yeah.
Because building and deploying these ML systems in healthcare requires a deep understanding of both worlds, the clinical side and the technical side.
It's like trying to build a bridge without engineers and construction workers. You need both to make it safe and functional.
That's a great analogy. And then the challenges continue as we move to data annotation.
Data annotation, where we label the data,
Yeah.
right? Basically telling the machine what it's looking at.
Exactly. Ideally, we'd have those top-tier clinicians, like, experienced radiologists doing the labeling, but they're already so busy.
So what happens when we can't get those experts?
Well, that's when those vulnerabilities start to creep in. The paper talks about the issue of ambiguous ground truth.
Meaning?
Well, even among experts, there can be disagreement, on a diagnosis. So the labels themselves can be subjective.
Oh, I see. So it's not always black and white.
Right. And that opens the door for manipulation. Like someone could intentionally introduce incorrect labels to mislead the model.
Whoa, that's scary, like someone tampering with the answers on a test.
Exactly. And then there's the issue of improper annotation, where the labeling process itself isn't done carefully enough.
So it's not just about getting the right labels, but also making sure the whole process is done right.
Right. We have to consider privacy, legal issues, all those nuances. The paper also points out that many healthcare data sets have what are called coarse-grained labels,
Gorse brain.
meaning they lack detail. They're not granular enough, which creates a bunch of problems. Well, for starters, the data sets used to train these models are often too small, and certain conditions, especially rare ones, might be underrepresented.
Ah, so it's like trying to learn a language from a dictionary that only has a few words.
Uh-huh, good analogy. And because of this imbalance, the models can become biased, making inaccurate predictions.
So it might be good at identifying the common stuff, but miss the rare stuff.
Exactly. And then there's data sparsity, which is basically missing values in the data.
So we're dealing with incomplete information.
Exactly. And that can lead to both false positives and false negatives, which can be very serious in healthcare.
Right, like telling a healthy person they're sick, or vice versa.
Exactly. So, yeah, even if we collect and label our data perfectly, there are still challenges in the model training phase.
Which I guess we'll dive into after a quick break.
That's good.
We were just talking about all those vulnerabilities in data collection and annotation. It's a minefield out there. But let's move on to model training. I imagine there's some unique challenges there too, right?
Oh, absolutely. I mean, one thing that can trip you up is, well, improper training. Like not getting the parameters right. Things like learning rate, epochs, batch size. If those are off, your model might just not perform as well as it could.
Kind of like baking a cake, right? Wrong ingredients, wrong baking time. It might look like a cake, but taste awful.
Perfect analogy. But even if you get those basics right, there are some more, well, serious threats lurking. We're talking privacy breaches, model poisoning, even model stealing.
Okay, now we're getting into some spy thriller territory. Let's unpack these one by one, starting with privacy breaches. How can those even happen during training?
Well, think about it. To train those really sophisticated ML models, especially deep learning models, you need tons of data. And often that data is stored in, a central place like a cloud server. If that server isn't secure, well, someone could get in and access all that sensitive patient data.
Yeah, data breaches are a huge concern, especially with healthcare data being so sensitive.
Absolutely. And, things like federated learning, where you're trying to protect privacy by training on decentralized data. Well, it adds another layer of complexity, new security challenges that researchers are still trying to figure out.
So even with those fancy privacy-preserving techniques, data breaches are still a risk.
Unfortunately, yes. It's a constant battle. But let's move on to model poisoning. Now, that's a really interesting one.
Model poisoning. The name itself sounds ominous. What exactly does it entail?
So imagine this. Someone, a malicious actor, actually manipulates the training data itself. They inject these carefully crafted data points designed to mislead the model.
So instead of tricking a trained model, they're messing with the source itself.
Exactly. They're introducing vulnerabilities that will surface later when the model is actually being used.
Yeah.
For example, they could subtly alter medical images in the training set, making the model misclassify certain conditions.
I don't know, it's like a doctor being sabotaged with a faulty textbook during their training.
Yeah, that's a good way to think about it. And the consequences can be pretty dire, especially in healthcare where, an accurate diagnosis can be the difference between life and death. And then we have model stealing.
Model stealing? What's the point of that?
Well, there are a few reasons someone might want to steal a trained model. Maybe they want to use it for their own gain, like generating false medical diagnoses for insurance fraud. Or maybe they want to analyze the model itself to, uncover information about the training data.
So it's not just about protecting the data, it's about protecting the model itself.
Exactly. These trained models are valuable assets, especially in healthcare. You have to protect them just like you would any other sensitive information.
I gotta say, this is all pretty unsettling. It seems like every stage of the ML pipeline is vulnerable in some way.
It's definitely challenging. But the good news is that the paper also talks about solutions, which we'll dive into later. But for now, let's move on to the deployment phase.
Deployment. So our model is trained, it's safe from poisoning and stealing, and now it's ready for the real world. What could possibly go wrong now?
Well, even with a perfect model, the deployment phase can throw some curveballs. One big challenge is what we call distribution shift.
Distribution shift. Sounds technical. Break it down for us.
It's basically a mismatch between the data the model was trained on and the data it encounters in the real world. For example, a model trained on medical images from one hospital might not perform so well on images from another hospital, especially if they use different equipment or imaging protocols.
Like a language barrier, right?
hmm
The model learned one dialect of medical data, but needs to be fluent in many to work in different settings.
Exactly. And this distribution shift can really mess with the accuracy and reliability of the model.
So can't we just train models that can handle those different data distributions?
Well, that's what researchers are working on.
Yeah.
The paper talks about things like transfer learning and domain adaptation. We can dive into those later if you're interested.
Definitely. Are there any other deployment vulnerabilities we should be aware of?
Another tricky one is incomplete data. In the real world, things aren't always neat and tidy. You might have missing values in your data, like an electronic health record with some fields left blank.
It's like trying to solve a puzzle with missing pieces.
Exactly. And when an ML model encounters that incomplete data, it might make the wrong predictions, leading to those false positives or false negatives we talked about earlier.
So even with a perfectly trained and secure model, messy real-world data can still trip us up.
It sure can. This really emphasizes how important data quality and completeness are throughout the whole process, not just during training.
It's like a chain, right? If
Yeah.
one link is weak, the whole thing can break. So we've seen how complex it is to deploy ML in healthcare. It's not just about building a fancy algorithm.
Nope, it's about the whole pipeline, from data collection to deployment, and being aware of those potential vulnerabilities at every step.
Speaking of steps, I guess we've arrived at the testing phase of our ML pipeline journey.
We have. After deployment, we need to test, see how the model performs in a real clinical setting, putting it through its paces with real patient data.
But even at this stage, there are still potential vulnerabilities.
Oh, yeah, you can't let your guard down. One thing to watch out for is misinterpretation.
Misinterpretation. How can that happen if the model is working correctly?
Well, even the best ML models have limitations, right? And we have to be careful not to overinterpret their output. If we blindly trust those predictions without considering other factors, we can make the wrong diagnosis or treatment decisions.
So the model is a tool, not a replacement for human judgment.
Exactly. The model provides insights, but it's up to the clinicians to interpret those insights in context. Look at the whole picture.
That makes sense.
Yeah.
Are there any other testing vulnerabilities we should keep in mind?
Well, those false positives and false negatives we talked about earlier, those can still pop up during testing. If there were issues in the previous stages like data sparsity or model bias.
Right, so those problems can carry over.
Exactly. And if you see a lot of those false positives or negatives during testing, well, it might be a sign that you need to go back and revisit those earlier stages, figure out where things went wrong and try to fix them.
So even in testing, we might need to loop back and make adjustments.
It's not always a linear process. It's more like, a cycle of continuous improvement. Always refining, always learning.
This has been incredibly insightful. I mean,
Yeah.
we've really gone deep into the potential pitfalls of the ML pipeline in healthcare. It's clear that building and deploying these systems responsibly takes a lot more than just, building a fancy algorithm.
Couldn't agree more. It's about the entire ecosystem, the whole process, and recognizing that each stage has its own set of challenges.
So now that we've explored the challenges, I'm really eager to hear about the solutions being developed. How can we actually make these ML systems more secure, more private, more robust? That's what I want to know.
Well, luckily, researchers are on the case, and there's some really fascinating work being done in this area.
Welcome back to our deep dive. We've covered so much, from the potential of ML in healthcare to, well, all those potential pitfalls lurking in the shadows. But
Yeah.
it's not all doom and gloom, right? There's got to be some light at the end of this tunnel.
Oh, there absolutely is. I mean, researchers aren't just sitting around twiddling their thumbs. They're actively developing solutions to make these ML systems more trustworthy. And it's a really exciting area of research.
Okay, good, because I was starting to get a little worried there. So where do we start? What are some of the key areas where progress is being made?
Well, one big focus is privacy-preserving ML. I mean, that's got to be a top priority, right? We're dealing with people's health information here, their most sensitive data.
Absolutely.
Mm.
So how do we make sure that these ML models can learn from all this data without, compromising patient privacy? That seems like a tough nut to crack.
It is, but there are some really clever approaches out there, like cryptographic methods, for example. They allow you to actually perform computations on encrypted data without ever decrypting it.
Wait, hold on. That sounds like something out of a magic show. How can you possibly do calculations on scrambled data?
It sounds counterintuitive, but it's totally possible.
Mm-mm.
One technique is homomorphic encryption. Basically, you encrypt the data using a public key, and only the person with the corresponding private key can decrypt it. But even in its encrypted form, you can still do math on it.
It's like having a locked box. You can shake it, weigh it, maybe even poke some holes in it, but you can't see what's inside.
That's a great analogy. Another cryptographic approach is called garbled circuits. Imagine you have two people, each with their own secret data, and they want to compute some function on their combined data without revealing their individual inputs.
So they want to collaborate without spilling the beans.
Exactly. Garbled circuits make that possible. One party sends a garbled version of the function along with their input to the other party, and the other party can then compute the result using their own input and this garbled circuit without ever seeing the raw data from the first party.
It's like having a trusted middleman who can perform calculations without knowing the specifics of what they're calculating.
Precisely. There are other cryptographic techniques too, like secret sharing, where you split a secret into multiple parts and distribute them among different people. The secret can only be reconstructed when all the parts are brought back together.
Like those spy movies where you need multiple keys to launch a nuclear missile.
Exactly. And then you have things like secure processors, like Intel's SGX. These are special chips that are designed to protect sensitive computations.
Like having a fortress within your computer, keeping your data safe from prying eyes.
That's a good way to put it. But it's not just about cryptography. The paper also talks about differential privacy.
Differential privacy, right? I've heard of that.
Right.
It's where you add a bit of noise to the data to protect individual privacy.
Exactly. You add carefully calibrated noise so you can still do meaningful analysis. But if someone tries to extract information about a specific individual, that noise makes it impossible to re-identify them.
It's like adding static to a radio signal, right? You can still hear the music, but you can't pick out the individual instruments.
Perfect analogy. And differential privacy has some great advantages. It provides group privacy, meaning it protects not just individuals, but also groups of people with similar characteristics. It's also composable, so you can combine multiple differentially private analyses without weakening the privacy protection. And it's robust to auxiliary information, meaning even if an attacker has some extra knowledge about the people in the data set, the noise still protects their privacy.
So it's like a security system that's designed to withstand even the most determined attackers.
That's the goal. And then there's federated learning, which is gaining a lot of traction as a solution for privacy-preserving ML in healthcare.
Federated learning, right? That's where you train models on data that's distributed across multiple devices without ever centralizing that data.
Exactly. So instead of sending all the raw patient data to a central server, the model is trained locally on each device, and you only share the model updates the parameters. The actual data never leaves the device.
It's like having a bunch of chefs working on a recipe, each with their own ingredients. But they only share the final dish, not the individual components.
I like that. And this is particularly appealing for healthcare because you can leverage data from multiple hospitals or clinics without compromising patient privacy.
So you can train more powerful models without creating these big, vulnerable data repositories.
Precisely. And there are tools like TensorFlow Federated that make it easier to implement these federated learning solutions. So we're seeing some real progress here.
This is all very encouraging. But what about those other vulnerabilities we talked about, like adversarial attacks and model poisoning? Are there solutions for those too?
Of course. The paper goes into those as well. It talks about countermeasures against adversarial attacks, which are basically attempts to trick ML models by subtly manipulating the input data.
Like those examples where you make a tiny change to an image and suddenly the model sees something completely different.
Exactly. And the paper categorizes these countermeasures into three main approaches. First, you can modify the model itself to make it more robust.
So it's like reinforcing a building to make it earthquake-proof.
Exactly. One technique is called defensive distillation, where you transfer knowledge from a larger model to a smaller, more compact one that's harder to attack. And then there's network verification, where you basically check the model's properties to make sure it's behaving as expected.
So you're putting in safeguards to prevent the model from being tricked.
Right. There are other model modifying techniques as well, like gradient regularization, which makes the model less sensitive to small changes in the input data.
So even if someone tries to tweak the data a little bit, the model's output stays stable.
Exactly. The second approach is to modify the data itself.
So instead of changing the model, we change the data.
Correct. One technique is called adversarial retraining, where you train the model on a data set that includes both normal examples and adversarial examples.
Yeah, so it's like a boxer training against different opponents, so they're ready for anything.
Haha, good analogy. There are other data modifying techniques too, like input reconstruction, where you clean the adversarial noise from the data before feeding it to the model.
Like having a security checkpoint that filters out the troublemakers,
Exactly. And then the third approach is to add auxiliary models to the system.
bringing in the reinforcement.
Right. One technique is adversarial detection, where you train a separate model to specifically identify adversarial examples.
Like having a guard dog that can sniff out intruders.
I like that. You can also use what's called ensembling defenses, where you combine multiple defense strategies.
So we're throwing everything we've got at these attacks.
That's the spirit. The paper also explores using generative models, like GANs, to either clean adversarial examples or generate new data to train more robust models.
It's like having an AI artist on our side creating counterattacks against these adversarial manipulations.
That's a creative way to put it. But beyond all these countermeasures, the paper also stresses the importance of causal models in healthcare.
Causal models, what makes them so special?
Well, causal models go beyond just identifying correlations in data. They try to understand the underlying cause and effect relationships. And that's really important in healthcare because it helps us answer what-if questions. What if we change this treatment? What if we intervene at this stage?
So we're taking machine learning beyond prediction and into understanding.
Exactly. Techniques like counterfactual Gaussian processes and probabilistic graphical models are used to build these causal models. And then to address those distribution shifts we talked about earlier, the paper explores transfer learning and domain adaptation.
Right, so we can take a model trained on one data set and adapt it to work on a different but related data set.
Exactly. Transfer learning is a broader concept, while domain adaptation specifically focuses on handling those shifts in data distribution. And these techniques are crucial for building ML models that are adaptable and reliable in different healthcare settings.
It's like teaching a translator to handle different dialects of the same language.
Perfect analogy. But all these technical solutions are just part of the story. The paper also really emphasizes the need for responsible ML in healthcare.
Right, it's not enough to just build these systems. We have to make sure they're used ethically and effectively.
Absolutely. The paper talks about some general principles for responsible AI, like human-centered design, using the right evaluation metrics, and carefully checking the data for biases.
So it's about considering the human element, measuring the right things, and being aware of those hidden biases that can creep into the data.
Exactly. And specifically in healthcare, the paper highlights the need for interdisciplinary teams that include clinicians, technologists, patients, and other stakeholders.
So bringing together experts from different fields and even involving the patients themselves in the process.
Right. This collaborative approach is essential for ensuring that these ML systems are designed, tested, and deployed responsibly.
Well, this deep dive has been quite a journey. We started with all the promise of ML in healthcare, then we delved into all the potential pitfalls, and now we've explored some of the solutions that are being developed. It's a rapidly evolving field, but one thing's for sure, ML has the power to transform healthcare, but we need to do it carefully and responsibly.
I couldn't agree more. It's all about finding that balance between innovation and safety, pushing the boundaries while making sure we don't compromise patient privacy or well-being.
Well said. A big thanks to the authors of this paper for such a comprehensive overview. It's given us a lot to think about.
It certainly has. It's clear that this is a multifaceted issue with no easy answers, but the ongoing research and the collaborative spirit in the field give me hope that we're moving in the right direction.
Me too. To our listeners, if you're interested in learning more, we highly recommend checking out the full survey paper. It's definitely worth a read. And until next time, keep exploring, keep learning, and keep diving deep.